In this part 3 video, we look at how OpenShift Virtualization use PowerStore Metro volumes for active high available storage. We will start by logging into the Bastion node, which acts as a secure entry point into our environment. We will verify the access to the OpenShift cluster and confirm that the cluster is reachable and healthy. In this setup, the Kubernetes control plane is running at the following API endpoint. After confirming access to the cluster, we will validate the cluster health by checking the nodes. We will verify node names, node status, node roles. Now, let us verify the CSI driver in the OpenShift cluster. The CSI driver is what allows OpenShift workloads to use PowerStore storage seamlessly and dynamically. When we check the PowerStore namespace, we can see that both the controller pods and the node daemon set are running successfully. As part of the CSI deployment, we also provide a configuration file that lists the two PowerStore systems the cluster connects to. This allows every OpenShift node to communicate with both arrays, and this setup is what we call a uniform topology. Now, let's quickly take a look at the UI of both PowerStore systems that are part of our Metro Volume setup. The first system is the one with the management IP ending with .60. This is PowerStore System A. Next, we have the second system with management IP ending with in .70, which is PowerStore System B. These are the two arrays we referenced in CSA configuration file. Let's take a look at the storage class that we use for creating Metro volume based persistent volumes. This storage class is named PowerStore Metro and it uses PowerStore CSI provisioner to create volumes. In the parameters section, we specify the primary array ID. We set the replication mode to Metro. We also specify the remote system indicating which secondary array participates in the Metro pair. With this configuration, any PVC created using this storage class will automatically provision a PowerStore Metro volume across two arrays. Let's deploy the OpenShift virtualization operator. From the OpenShift console, go to the operator hub and search for OpenShift virtualization. Click install and proceed with the default settings. Once installed, create the hyperconverged resource to enable virtualization. When the status shows available, the deployment is complete. Next, let's deploy a basic virtual machine using an ISO image. From the OpenShift console, go to the virtualization and select Create Virtual Machine. Choose the option to create a VM from an ISO. Review the CPU, memory, and network settings and keep the defaults for basic deployment. Provide the name of the VM. Under storage, change the storage class to PowerStore Metro to ensure Metro volume provisioning. Click Create Virtual Machine. Once the VM status moves to running, the VM is successfully deployed using an ISO on PowerStore Metro storage. On this virtual machine, I have deployed PostgreSQL and configured it for testing. Using pgbench, I have loaded sample transactional data into the database. This setup will help validate the behavior of the VM and storage during the upcoming test scenarios. The PostgreSQL virtual machine is deployed in the VM namespace. It is running on node VM02 and the VM's internal IP is 10.128.0.59. From the Bastion node, I inspect the PVCs in the VM namespace. Here, we can see multiple persistent volume claims associated with this VM. For PostgreSQL data, we are interested in the PVC whose names ending with 8CF6. This is the volume where the Postgres data directory is stored. Since this PVC uses Metro storage class, the underlying volume is created as a PowerStore Metro volume, which means it exists on both PowerStore arrays. Here, on the first array with the management IP ending with .60, we can see the Metro volume and its attributes. And on the second array with the management IP ending with .70, we see the same volume synchronously replicated and fully in sync. On the BM02 node, we inspected the multipath configuration for the volume associated with the PostgreSQL VM. In the multipath listing, we can see multiple active ISCSI paths grouped under the same device, mpath-c. Each path has a priority value and multipath automatically uses the highest priority path for I/O. All the paths share the same UUID, which uniquely identifies the metro volume across the PowerStore arrays. Here in the ISCSI session output, we can see 4 active sessions established from this node, 2 from PowerStore System A, 2 from PowerStore System B. In this test, we validate how the workload behaves when the primary storage path fails. I have loaded the PGBench data and now I am running 10-minute test. At the 5-minute mark, I'll disconnect the network to PowerStore system A to simulate a primary path failure. In BM02 node, before running the test, we check the multipath status. All four ISCSI paths are active and mapped to M path AC, with the highest priority path being used for I/O. The test is running. Let's quickly check the PowerStore metrics to see live I/O activity. Now, when we check the metrics on PowerStore system A, we can see active I/O being recorded. This is because the workload is currently using the metro volume paths from system A, which have the highest priority. If we look at PowerStore system B, we don't see any I/O activity at this moment. That's expected because the host is actively consuming the volume from system A due to the highest priority paths. The test started and it has been running for 5 minutes. I have disconnected the network to PowerStore system A. As soon as the active path drops, there is a brief freeze, which is expected while multipath detects the change. Now, when we check the multipath status on the BM02 node, right after the momentary pass, multipath marks paths to system A as faulty and automatically redirects all traffic to system B. The PostgreSQL VM stays healthy, the volume remains mounted, and I/O continues without interruption. Let's check the PowerStore metrics again. On PowerStore System A, we now see no I/O activity, which is expected because the paths to System A were disconnected. If we look at the PowerStore System B, we can now see the activity I/O being recorded. This confirms that all traffic has successfully shifted to System B and the metro volume is being served entirely from remaining active paths. The 10-minute test finished successfully and there were no transaction failures recorded. Now, let's take a look at overall metrics to review how the system behaved throughout the test. OpenShift shows stable CPU throughout the run, and both the network and storage metrics remain healthy. After that momentary freeze, network bandwidth and packet rates stay steady with no packet drops, and storage layer continues operating normally through the transaction. Overall, this test confirms that PowerStore Metro Volume provides high availability. When the paths to one systems are disconnected, the host automatically redirects I/O to the other system, keeping the application fully available. The combination of Metro Volume, ALUA multipathing, and CSI integration ensures resilient and reliable storage access for critical workloads running on OpenShift. In this test, we validate how the workload behaves when the primary storage paths are restored. I have started the 10-minute PGBench test again, and at the 5-minute mark, I'll restore connectivity to storage system A to begin the failback. In BM02 node, before the failback, we check the multipath status. All active I/O is currently flowing through the paths to system B because system A was unavailable. The test is running. Let's quickly review the PowerStore metrics to see live I/O activity. Now, when we check the metrics on PowerStore system A, we don't see any I/O activity. This is expected because before failback, the workload was running entirely on system B. If we look at PowerStore system B, we can see active I/O being recorded. That's because the host is currently consuming the metro volume from system B as system A is unavailable. The test now at the 5-minute point, I am restoring the network connection to PowerStore system A. We simulate the failback event by reconnecting the network to PowerStore system A. As soon as the paths come back, multipath detects them immediately. This time, there is no freeze because new requests naturally shift to the preferred paths while any in-flight I/O continues on the existing ones. This transaction is seamless. Next, when we check the multipath status on the BM02 node, we can see that the paths to system A are now active again and marked with highest priority. I/O has switched back automatically and system B paths have returned to standby. Now let's check the PowerStore metrics after failback. On system A, we can now see active I/O being recorded again, while on system B, I/O drops to zero. This is expected because system A has resumed its preferred role. At the end of 10-minute test, there are no transaction failures recorded. The workload continues normally throughout the failback event. In OpenShift console, on the left, we have the failure graph, and on the right, we have failback graph. You can see that during failback, OpenShift continues to show steady CPU usage, and both the network and storage metrics remains healthy, very similar to what observed during failover. However, unlike failover, where a brief pause is expected as path switch, the failback path restoration is completely seamless. New IO immediately moves back to the preferred paths on system A, while in-flight requests continue on existing paths with no interruptions. This side-by-side comparison clearly shows that PowerStore Metro Volume not only handles path failures gracefully, but also restores preferred paths cleanly during failback, keeping the application fully available end-to-end. Overall, this test confirms that PowerStore Metro Volume restores preferred paths smoothly. Multipath automatically reroutes I/O back to system A without disruption, and the PostgreSQL application remains fully available. Metro volume, ALUA, multipathing, and CSA integration together ensure seamless storage connectivity even during failback operations.